Right, so in this video, we're going to take a look at zeros of polynomial functions. So the first thing we need to look at is the fundamental theorem of algebra, which says if f of x is a polynomial of degree n, where n is greater than 0, so you have to have at least a linear function, then f has at least one 0 in the complex number system. Then we get to the linear factorization theorem that says if f of x is a polynomial of degree n, where n is greater than 0, then f has precisely n linear factors, where c1, c2, all the way up to cn are complex numbers. So these theorems are what we call existence theorems. They don't really tell us much about functions other than if you have this type of a function, then these kind of factors exist. So let's kind of get an idea of what this tells us. So 0 is a polynomial function. So if we look at a first degree polynomial function, f of x equals x minus 2, it's a first degree function and it has exactly 1 0. If we looked at this third degree polynomial, x cubed plus 4x, we have 3 zeros, and those zeros are going to be where x equals 0. So we have x equals 0, which you get from this particular one there, or x equals 2i, or x equals negative 2i. So here we do have a couple of complex solutions there. So let's look here, a couple of quick examples here. How many zeros do each of the following functions have, and what are they? So here we have a quadratic function. We have f of x equals x squared minus 6x plus 9. And in this case, if we factor this, we'll get that f of x is equal to x minus 3, x minus 3. This is a repeated 0, but there's still 2 zeros, okay? And those zeros are at x equals 3. Then if we look at the function in b here, this is actually a difference of squares. So this factors as x squared plus 1 and x squared minus 1. X squared minus 1 and x squared plus 1 can both be factored, and they factor in the form of x. So it'll be x plus I and x minus I, and then x plus 1, x minus 1. So we actually have 4 zeros here, which makes sense because it's a degree 4 polynomial, and our zeros are x equals negative I, negative 1, and positive 1. So again, degree 4 polynomial has 4 zeros. Right, so we can also do something called the rational zero test. So if the polynomial f of x has integer coefficients, so no fractions as coefficients, every rational zero of f has the form p over q, where p and q have no common factors other than 1. P is a factor of the constant term a0, and q is a factor of the leading coefficient a sub n. So your possible rational zeros are each of the factors of the constant term over each of the factors of the leading coefficient. Now, this is not to say that there are only rational zeros. What this says is that if any rational zeros exist, they are of this form. There could still be irrational zeros, like the square root of 5, or there could still be imaginary zeros, so complex numbers. However, this is just saying that if rational zeros exist, they will be of this form. Okay, so let's take a look at what this is going to mean here. So in the first example, find the rational zeros of f of x equals x cubed plus x plus 1. So your constant term here is 1, and your leading coefficient is also 1. So you have 1 over 1, which is 1. So your possible rational zeros are either positive 1 or negative 1. Like, those are the only rational zeros that we could have. So if we substitute those in to find our values there, they would be zeros if f of 1 or f of negative 1 equaled 0. But if you look here, f of 1 is 3 and f of negative 1 is negative 1. So in this case, neither of these is equal to 0, so f of x has no rational zeros, because those are the only possible zeros that there could be. And again, this is not to say that there are no zeros whatsoever. It's to say that if any zeros exist, they're either complex or they're irrational. And in this particular case, I believe that the 0 is irrational. Okay, so find the rational zeros of f of x equals x to the 4th minus x cubed plus x squared minus 3x minus 6. So because the leading coefficient is 1, the possible rational zeros are the factors of the constant term. So your factors here are going to be, because that constant term is 6, your factors, or your possible factors, are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And this all happens because you had all of the factors of 6 over 1. So 1 over 1 gives us 1, 2 over 1 gives us 2, 3 over 1, 3, and 6 over 1, 6. And again, you have to have the positive and negative values there. So you're now looking at 8 values to test. And you could test all of these rational zeros. We're not going to do that at this point. What I am going to do is just tell you that in this case, if you do test them, you get rational zeros at x equals negative 1 and at x equals 2. And you can go ahead and substitute those values in for x and test and verify that you do get zeros. But these are the two that we have. And this is another one of those cases that you could either use substituting those in, or you could use repeated synthetic division to test these. All right, so here we're going to do a rational zeros test. So we can determine that the possible rational zeros are your factors of 3 over your factors of 2, because 2 is your leading coefficient. So fortunately for us, we either get plus or minus 1, comma, plus or minus 3 over plus or minus 1, comma, plus or minus 2. So we either get 1 over 1, so plus or minus 1, 3 over 1 will get us plus or minus 3. And then 1 over 2, plus or minus 1/2, and 3 over 2 will give us plus or minus 3/2. So we can go ahead and test one of these. So let's do this by synthetic division. So I'm going to test by synthetic division positive 1. So we'll put a 1 here in the box. And then we have our coefficients come from our original f of x. So 2 3, negative 8, and 3. So we'll do our, bring down the 2, and then 1 times 2 is 2. We add 3 plus 2, that's 5. 1 times 5 is 5. Negative 8 plus 5 is negative 3. Times 1 is negative 3. And that does give us 0 here. So this is indeed a factor. Okay. So we have here, oops, that we can write our function as x minus 1, because this 1 is a factor, times 2x this would be squared plus 5x minus 3. And then by factoring, so we get 2x and x, so plus 3 here and a minus 1 there. So by factoring, we get that our other rational zeros are actually going to be, we have x equals 1, x equals 1/2, and x equals negative 3. And if you know, all of those were possibilities up from the top. So not every possible rational zero is in fact a rational zero, but any rational zeros that you do have will indeed come from that list.